most of you went through the problems and the solutions of this final exam at least once. And I said your final exam will be posted the day after tomorrow, will be similar to this in the format and in the technical content, but it will be slightly more difficult than this in some sense. And maybe I add some additional things, okay, because you already went through this and we are reviewing this today, so you will have enough knowledge to tackle the take-out final exam, okay. Exam, the purpose of exam is to test you, is not to assess your educational potential, something like that. I want to teach something through the exam, okay? So try, do your best to get correct answers, okay? I think I said once this was the final exam for the senior student 2 years ago. So they solved the same problem within 100 minutes. Of course, they didn't do well, and the average score of their average score is 20, 30 something, okay? Miserable, okay? Right? But if you practice this, and then you will be improved in engineering skill and how to apply your knowledge to the practical problems. Okay, that is the real value of engineering. Okay, so this will help you. And the first problem is I prepared the 3 Bode plus, and these Bode plus are generated by computer. So this is not the asymptotic plot. This is the real Bode plot. Okay, and you have 3 different plots, and each plot has 2 problems associated with it. First one is, this is input to output transfer function of the sum feedback system. And from this, the question is crossover frequency and phase margin of the loop gain is the problem number 1. And problem number 2 is to sketch the output waveform of in response to step unit increase in the input voltage and so on. Okay, so if we see this problem first, you may wonder how this thing is related with the loop gain and phase margin of your system. Okay, but every hint is here. So this is the input to output transfer function. So we are using the concept and the term of equivalent second order system. We are saying that all the feedback system can be simplified equivalent second order system. In that, we are talking about only input to output transfer functions. Okay, so disturbance to output transfer function is entirely different story, and you need other skills, and don't fix that. Okay, many people think the higher crossover frequency will improve speed of something, or something there will be only input to output transfer functions, and you will see other transfer function. I mean the time domain response corresponding that particular transfer function is not related with this loop gain crossover frequency at all. Okay, you will see that example. So this is input to output transfer function, and I sketched this. Okay, so you may need the ruler, small ruler, to solve the final exam problem. And this is -1 slope, and this is -2 slope. So if you watch this is 0.1, and this 1 and 10 kilohertz, then slope is -40 dB per decade in this region, and -20 dB decade in this region. Okay, so this is generated from the transfer function. So this is the real Bode plot. Okay, and we assume that this has this -1 integration structure, okay? If the plant is very complicated and you need poles and zeros, many poles, 2 poles, 2 zeros, or something like that, and integrator, but assume using proper compensation, this is shaped in this manner. That is always possible, right? If there is no integrator, you add the integrator in the compensation. There are poles and zeros, something strange in between. You try to cancel them. So to make this loop gain, this shape, it's called loop gain shaping. Okay, this concept includes the stupid PID type discussions. Okay, some absurd idea. This is the overall thing. It can be generalized to any feedback system. So assume somehow you obtained this -1 slope structure. Okay. For that case, loop gain is this one. This is loop gain expression. And this is the exact expression of input to output transfer function. And this is asymptotic analysis. I said this is another approximation. This is engineering notation. This is 1, this is LS, loop gain, and this is valid for the frequency below, loop gain crossover frequency, which is this one, actually. And this is, and omega C is this frequency. It's converted to omega n, and at this frequency, we have this peaking, okay? Then this peaking, from this peaking, you can obtain the phase margin of the loop gain. Okay, if this is true, you have this type of loop gain transfer function. Input to output transfer function is this one. So at frequency below crossover frequency, just this is 0 dB line, which is 1, and after this follows this one. It follows the loop gain slope. So this is this -2 slope. And here you have peaking, okay? This is a typical feature of second order system, and the magnitude of peaking is given by this, okay? We derived this from very elementary geometry, okay? I think I first derived this. I don't know, maybe somebody else derived this in height, so I cannot find him. But as far as I know, I derived this by myself, and from this you calculate this and this, okay? So this is a loop gain crossover frequency, 0 dB crossover frequency, and this is related with phase margin. This is the peaking, and relationship with this, solving this equation, you obtain this value and this value. That is the answer to the question number 1. And question number 2 is sketch YT in response to the step unit increase in input voltage. Okay, in input voltage is important. Something else is different. Then you cannot solve this with this information. But input to output is obvious. So this is, you transfer this into time domain expression. Okay, then that is the standard form. So in chapter 5, we learned that, okay? And the only problem is this phase margin should be converted into zeta, but we have this expression. This is peaking due to the some phase margin, and this is the peaking due to the zeta, and they should be the same, okay? Then this is the relationship, and the zeta is this 0.16, okay? Then you have formula, maximum peak is this one, okay? And with this, this is 1.73, and the final value is 1, okay? So there is no steady state error in step input response, and this is showing the exact command tracking in the steady state, right? And this is given by this 3 divided by zeta omega n. Okay, this is given by the solution of standard second order system. But this is nothing more than we are assuming this is exponential curve, then this is the time constant of exponential curve. And 3 times of the time constant is 5% bound settling time of this response. Okay. So there shouldn't be any problem. And if you take correct approach, okay. And the second Bode plot is shown here. I said this is another loop gain plot of another feedback system. So it starts with this -1 slope, and it went to 0 slope, and it come back to this -1 slope. Okay, this is the loop gain of some strange system. Usually, you don't want this. Okay, the ideal loop gain characteristic is this one, -1 slope up to this crossover frequency. Okay, that is not always possible because of something, the dynamics of a plane. That is not always possible, but we are trying to make the loop gain very closely resembles this structure, -1 structure. Okay, that is the one purpose of loop gain shaping. But for the purpose of generating problem, I assumed this. Okay, then you know this. This is looking at this 500. Okay, if you use some strange ruler, it will be 400 or 600. They're okay. They're the same. Okay, so try to use this ruler at least. In the past, the undergrad student, I told them bring the ruler, but they didn't bring it, and they just draw line arbitrarily. But I considered within 20%, everything is okay. Okay, but try to use this. This ruler is very important in this Bode plot related analysis. So this has initial, this integrator, and there is a 0. Okay, this is 0, and this is pole. All right. So 0 is coming first, and pole is this pole is coming later, and this frequency is this one. This one, something similar to this number is okay. Okay, and phase is approximately -45 degree, 0 degree, -90 degree, -45 degree, so on. And the final phase is -90 degree. Okay, of course this is approximation, but this is good engineering practice. At the corner frequencies, the phase is something in between. Okay, so -45. Use this number. Is a good approximation. Why use other numbers? Okay, this is the best number to select, right? And first one is steady state error, ESS error, due to step unit and step lamp function and step parabola function. Okay, and at that time I repeated this derivation of steady state error. So we skip this, and the final form is this one. The final form of this ESS is given by this for the older system. Okay, so this is the input, Laplace transformed version of input, and this is loop gain, and this is what final value theorem of Laplace transformation. For the step unit, you just use 1/s, and the SS they cancel. All right. Then you evaluate this at 0. Then you have this original integration, and this pole and 0 has terms, but these terms reduce to 1. All the terms other than this initial integration, it becomes just 1 because we are using S of 0. Okay, for the final value theorem. So this is very trivial. There's nothing to remember or nothing to memorize. Okay, for the step input unit, this one is true, and for this we have this initial -1 slope. Then this becomes what? Infinity. Then this becomes 0. All right. For the ramp function, this becomes S squared. Okay, then we cancel this one, and this becomes 1 divided by 1 plus L. Loop gain 0 is Km divided by S, and as S is still alive, okay, then S cancels, and this is 0. It goes inside of this parenthesis. The remaining is Km, all right? And all the other terms becomes unity. They go away, okay? So the answer is, for the lamp unit, it is this one. Km is this number, integrated gain. So this is the answer. And for this, you have another S here. Then S goes to 0. Everything, the whole thing goes to infinity. That's obvious, right? So this is the result, right? And second problem is plot the polar plot of loop gain. So this loop gain is given. So initial phase was minus 90, and magnitude was very large. It starts down there and goes up. And during this period, during this midband, the phase is increasing. So minus 45, and I typed 0 degree, but it nearly does not go to 0. It approached to something like this, because the frequency is, distance between frequencies are finite. If they are infinite, it goes to 0 in somewhere, all right? But they are finite, so it is doing like this. So phase is somewhere here, and at this frequency, 20 radian per sec, and 2000 radian sec, we assume this is 45 from the Bode-Plus sketch, and when this reduces to 1, so it encircles unit circle. This value is 3 times 10 to 4, okay, 30 kilohertz. That's 30 kilo radian per sec, okay, and the phase is minus 90, so it's sliding up along with this vertical axis here, okay. So this is the polar plot, okay. So you should know this at least, okay. You don't have to know every details about the transforming from Bode plot to polar plot, or plotting this polar plot of every transfer functions, okay. That is not necessary, but you should know the idea of this, okay. And here I said mark the phase margin and the gain margin, something like that, okay. What is the definition of the gain margin? Gain margin is how much gain can be increased while maintaining stability. This system is obviously stable, right? So how much you can increase? If you increase the gain while phase is fixed, the shape remains the same, and this shape, this curve just expand out. So it expand out like this. It never encircle this point. Okay, that means gain margin is infinity. By increasing only gain, you cannot destabilize this system. That is the answer. That is the message from that. And phase margin, this is fixed. This shape is fixed. You are locating this. If you locate this minus 90 degree, then this point goes to here, and the system starts to start oscillating. That phase margin is 90 degree, okay? You may wonder how you introduce 90 degree phase. Just add one pole. Then eventually that will include the phase delay by 90 degree at infinity frequency. If you use integrator, another integrator, then phase will be delayed initially, okay, from the beginning. The phase starts somewhere here, minus 180. There you add another integrator, okay? If you add another pole, the phase margin will, the phase delay will depend on the location of the pole, but finally it will increase phase by 90 degree, okay? So suppose you have gain margin of the T2, 6 dB. If you double the feedback gain magnitude, the system becomes unstable, okay? you have 45 degree of phase margin. Then if you add integrator, one more integrator, definitely the system is unstable. If you add one pole, that depends on the location of the pole. Okay, it can be stable or unstable, but very dangerous. All right. So that is the meaning of the phase margin and the gain margin. I said remember the meaning of the margin. Okay. If I ask what is the gain margin, phase margin, they start talking about the Bode plot and the phase of the frequency of the phase minus 180 degree and distance between 0 dB. That is really bad answer. Okay? This is the margin. How much margin can be added? How much phase delay can be added is the meaning of the gain margin and the phase margin. Easiest one, and just the term margin is playing a role there. Okay, another Bode plot. This one is what? This is some transfer function, right? This is disturbance to output transfer function. Okay, D stands for disturbance. So disturbance to output transfer function is something like this. All right. This is the typical shape of disturbance to output transfer function, and the input to output transfer function is always this second order low pass filter. But disturbance to transfer function is something else. Okay, entirely different. This low pass filter characteristics. Right? Then, if disturbance to output transfer function is low pass filter, you are in deep trouble. Okay? Noise is amplified. Noise is playing the role of the input command, which is a disaster. Right? So this type is the typical shape of this disturbance to output transfer function. So I generate using some transfer function, and you estimate what kind of transfer function I used, right? So this is the initial slope, and if you calculate, if we just watch this is 20 dB for plus 20 dB per decade, and this is the minus 20 dB per decade, and this is very similar to the horizontal line. So I used initial integration, and I used one pole and another pole here. The pole frequency, you draw this line, and draw this line and identify the crossing point. That is more than enough. Okay, this number can be 700 or 900, even 1,000. It really doesn't matter. Okay, so with this, all right. And input is this one. This is the input disturbance. Okay, so the DC is gain at low frequency. Zero frequency is what? Minus infinity dB. That is what? Zero. This DC point, this term is completely eliminated. Okay. At this frequency, this is 20 frequency. This is 20 hertz. This is 10 hertz, 20 hertz. There's minus 40 dB. So this sinusoidal component is reduced by 100 times. So it is the magnitude, and the phase of this slope is at this slope. This works as a differentiation, has plus 90 dB phase, and the T is missing here. So this is output response to this input, and to this input you need to take a look at this point, because this is 10 kilo something. So and take a look at this point, and the value is 1. So this is attenuated by this number. This is just the linear scale of minus 50 dB is this number, and the phase is minus 90 degree. So this number. This is gone, and you have only two sinusoidal components. So this Bode plot is providing all the information, complete information of linear time invariant system, including stability margins, phase margins, gain margins, and response to this sinusoidal waveforms, response to the noise component, and transient response is also evaluate from this frequency, this plot. Okay, that is the next question. And next question is sketch the step impulse response, step unit response of this output due to the step change in disturbance. Okay, transfer function of this, expression of this is very simple to calculate. So if you extend this line, it crosses this 0 dB line at this point. So with this, you have integration gain of this one, and you have a pole, okay? And this is the third order system, no, second order system. So this is integration, and integration gain comes here. Because you put this number here, that becomes 1. 1 is a 0 dB line, okay? So this is integration gain and one pole and another pole. And for this Laplace transformation analysis, you need to pull out this number and use this, and this becomes something very close to 20, and this is the equation. All right? This is the S-domain equation of this disturbance to output transfer function, and we are considering this step impulse response. So there is a 1 divided by S, they cancel, and you have this. Then you can perform this partial fraction expansion. So you know this formula, okay? And you can easily calculate this. And this one, from this one, you know this formula of inverse Laplace transformation of this simple form. Then output is given by this, okay? There is an initial value, positive value, and it has 2 exponential terms. But this is different. This is 80. This is 800, and this minus means exponential decaying terms. One is this one. You start from this number, positive of this number, and the other term start out from here. So they are decaying in exponential function, but time constant of this one is very fast, 10 times faster than this. So this term dies out much faster than the other term. So this is plus, this is minus. You add them one by one, term by term. You start from 0, and at this point, it is reduced very close value to 0, negligible value. Then this one start to follow this, and 5% boundary time constant is 3 times this pole. Okay, 1 over time constant, which one is this? So this time period is this one. So you can ignore this, except this one. Okay, find out the maximum value of this, which is very, very, very stupid question. Just is what? This is just the labor job. Okay, and this time constant and this value can be always calculated if desired, but it does not mean much. Okay. If you take a look at this time constant is determined by this one. This one, lowest pole, this is what? Called the dominant pole. So the effect of this is this decays very fast, all right? And somehow the coefficient is the same at this point, but other cases, coefficient of this term is much smaller than the other one. Okay, so it contribution of this fast decaying part is small, and they decay much faster, can be ignored in calculating this. Okay, so this is the result. Second problem is related with this Nyquist analysis. This is very strange in Nyquist plot. All right. So this occurs a lot in the textbook. Example, for the sake of example itself, it does not occur in practice. You will never see this in practice, but somehow this will help to understand the principle of Nyquist analysis along with causes analysis. Okay. So just paying attention on this just once is enough. This is not a good problem, so it won't happen in real cases. So many textbooks, they draw very strange this way, this pattern, and ask some riddle-like questions, some cues for morons. Okay, so that is stupid questions. All right, but anyhow, I use this, so this helps to understand the basic nature of this Nyquist analysis along with the Cauchy's theorem. All right, so I already prepared this. NO is the number of encirclement of this 0 point origin. This is number of encirclement of this -1 0 point. All right. So from 0, this encircles. You do this. You encircle this once here and go like this and go encircle this twice. Okay. So NO is twice, but direction is opposite to the clockwise direction. Is counter clockwise direction, opposite direction to the movement of the needle of the clock. So I use the -2. Okay. The easier way is it draw line from origin to the outside. Okay. So don't draw this way. Okay. So draw this way. Then there is a 2 intersection point, and intersecting this direction, you have number of -2. Okay. And this one minus from here to there are 2 intersections, but direction of intersection is opposite. Okay. This is clockwise direction, and this is counterclockwise direction. And you start doing like this. Then you come back to the original point without touching this. Okay. So n -1 is 0. Okay. For this case, this n 0 and the encirclement of this origin by this contour is only 1 in the counterclockwise direction, and this is also only, not only, this is 2, right? 1 here, okay? Then is -2, okay? All right, so this is about the loop gain, polar plot of the loop gain and encirclement of origin and minus point. And the Nyquist guy is relating this theorem to the stability of linear time invariant system. And the Cauchy's theorem originally talking about the encirclement of the origin and the number of poles and the number of zeros. Okay, Nyquist is something else. So it concentrates on this. So Nyquist analysis is focusing on this, right? And this Cauchy's analysis, actually this one is Cauchy's theorem, and LS is NS divided by DS, okay? And we have 2 systems, and system A and the system B. System A, this is assumption. This is given by problem. RHP0 in LS is 1. So LS is NS and DS, okay? And the using Cauchy's theorem, you can calculate the number of RHP poles in RHP plane of S plane using the encirclement of the origin, okay? Is the origin. So you know this. So this was -2 from the previous analysis, and this G is given. Then P becomes 3. Okay. So that means this denominator equals 0 has 3 poles in RHP. Is the meaning of this? This is nothing to do with this stability theory, but this can be considered as the intermediate step or the application of Cauchy's theorem. And this is a Nyquist theorem. RHP root is given by this, but the encirclement point is not origin, but this -1, 0. Okay? And this is given, P is given, and N is known. Okay? then n was -1, p is calculated here, then g becomes 3. Means there are 3 unstable poles in this characteristic equation. Because we are concerning about this equation, so this equation is our interest. Okay, LS, we don't care about LS. Okay, but this is part of this theorem. This is Cauchy's theorem, and this is the Nyquist theorem you are using directly. Okay, and perform the similar calculation for this case, and you have this. So this is unstable. G other than 0 is unstable, and for this case, G becomes 0. So the system is stable. G becomes 1 is unstable. Okay, understand this? So you distinguish between this and this. Okay, this is unnecessary, but this helps the relation to understand the relationship between Cauchy's theorem and the Nyquist theorem. Okay, all right, but this kind of situation never happen in practice. Maybe something similar to this, maybe just encircling once will happen. That really happens, but this is something artificial. Okay, but there are strange some. Forget about them. Okay. All right. So far we discussed equivalent second order system and Nyquist analysis, and the last two problem is very important. That problems, they deal with the design of compensation, and this is the heart of this course. Actually, you took this course to have the capacity of solving this, okay, and to apply this procedure to your own case. All right. So this is general. During the lecture, I said I only provided just one example, but that example is very typical one, so that can be expanded, okay, with some modification if necessary for general cases. And this is the problem, okay. So key word here is loop gain shaping. You are shaping the loop gain in the desired form, and in this problem, you will design feedback compensation for the loop gain specification or characteristics. 0 dB crossover frequency at 200 radian per sec and 45 degree of phase margin. 60 degree is okay, but 45 degree is good enough. And -20 dB decayed for the low frequency below omega c. So before loop gain crossover frequency, this -1 slope, straight line, is the best possible loop gain characteristic. So if you can achieve that, achieving that is obvious choice, okay? And the following questions, okay? So design and analysis of everything, okay? So let's go to the solutions. So spec was omega c as this one, and the phase margin of 45 degree and -20 dB decayed slope for the lower frequency below loop gain crossover frequency, and select the simplest structure. You may add and pole 0 arbitrarily and cancel them somehow. That's not answer, okay? That is really unnecessary. So use the simplest possible case. So this is the GS, okay? GS is given by this block, French block. So GS is, numerator is 1, and it has 2 poles. First pole is at 20 radian per sec, and the second pole is 200 radian per sec, okay? So to achieve this, you start with this integrator and make integrator gain at this point and cancel this 0, this unnecessary pole. So there are pole is existing in the middle, so it's cancelled. So to cancel this, you need add the 0, okay? So you need one 0, and the integrator to have integrated structure, and the integrate is selected at this value, then the integrator is going like this, and it has pole, so it will be changed -1 to -2. Then this is the corner frequency. Phase at this point will be 45 degrees. Okay. Then with this, the design goal is achieved. Right. Then implementation of this. This is a sine inversion, and this is a print, and this is a mixer, and this is a compensation. Why use this one? Capacitor is necessary to have integration function, and this R, resistor is necessary to implement the integration. All right. To have integration, you have capacitor somewhere 1 or 2 in parallel. You have R 1 or 2 in parallel. So you use this 10K. I said use 10K resistor as many as possible. So use 10K. Do not use some value. Okay. 10K is the most convenient one to use. If you use 10 mega ohm, you are in trouble. 10 mega ohm resistance is very maybe expensive, and they have wide tolerance. Okay, and this one is very easy to make and widely available. So use this. And why use this? This create what? 0. So you need 0, right? So, and this also provide the integration. So obviously this is the desired structure. This integrator plus 0 is implemented, and this is necessary integrator. Okay? If you use something else, it is impossible to realize this. Okay? You can place 0 here, then something will happen here. Okay? So this one, okay? And this can be simplified. Whole thing can be merged into one. OPM, I told you that many times. And select the values, okay? So from this is obvious, right? We know this. This pole is determined by this. Okay, not necessarily. In the past, I explained this. But later on, I found a better way of explaining. Already, I initially explained the structure of the G1 and G2 and the connection of the circuit structure to poles and zeros. Okay, I already explained that. So then this calculation is one necessary. All right. So you already know this is 0. This creates 0. So this is 0. Okay, and 0. And this C and R, 1 over this C and R is integrated gain, and this value is automatically determined. And there are 2 requirements here. One is integrated gain, and the other one is 0 frequency. But you have to select 3 components. You have only 2 equations. What you gonna do? Select one arbitrarily, okay? Then select the remaining things. That is the conventional way of doing this, okay? So select this one resistor of 10K somewhere. I think I already selected this. I already selected this in advance, okay? So then select this, then you do this simple calculation, and you can you can get this compensation. And the second problem is sketch the equivalent second order transfer function for this. So you already know this because it has this structure. It follows a 0 dB line. We are talking about input to output transfer function, and it goes this, and it has this picking, and the picking is this one. And from this picking, this is selected to be 45 degree, and the peaking is calculated, and from this phase margin you can evaluate zeta. Okay, so from the previous analysis, you know the omega n, which is omega c here, is 200, and the zeta is this one. So actually this is 20 log 1 over 2 zeta, and you get two expressions and solve them. You have this, so you know this, and this is the pole plot of the second order system. One is this, and the complex conjugate of this is here. This is omega n, is the radius of this semicircle, and this axis is actually cosine. This one is this one, and the sine, this angle is this one, So you have P1, P2, this one. Okay, complex conjugate pole pair here, right? This is the second problem. Third problem is derive TDS. Okay, derive TDS. So this plot is GS. This is GS, right? Then TDS is GS divided by LS for frequency lower than omega C, frequency larger than omega C. This one is GS, and I need the direction of this inequality. You know this, right? Oh, no, this is LS, right? No, GS, right, yes. You already know this, right? Okay. So input-output transfer function becomes 1 here. But in general, disturbance to output transfer function, there is not 1. It never becomes 1. It is this one. So GS divided by LS in linear scale, in log scale, linear scale becomes subtraction.
There are a lot of interferences in the continuous info. Maybe if you do mic at the center. No, at the center of your quad.
Okay. All of them?
Yes, just try this.
Really bad?
Yes. At some point, you can put it above.
Try. Okay, let's do the subtraction here. So this is open loop. In open loop GS, it starts from 0 dB, and it has for like this. And up to this point, it is subtraction. So this is subtract this much. Okay, and at this point, this was 0 dB, subtract by 20 dB. So it passes minus 20 dB here, and slope here is minus 1. Slope here is plus 1. I'm sorry, this should be plus 1. Okay, then they have this horizontal line, and it at this frequency they meet. Okay, this is a special case. Usually they don't meet. Okay, if they don't meet, then maybe this will be something like this or some changes. But this case, they meet, then it goes plus 1 slope here and 0 slope. And this is, it has pole minus 2 slope. All right? So there is a second order term because this was 0 dB and this was minus 2 dB. Then there should be a what? Peaking, okay? And peaking is determined phase margin at this point, okay? Phase margin at this point, right? And phase at this point was minus 45 degree, and so phase margin is 45 degree, right? So 45 degree is translated with zeta of this number. So you have formula somewhere here, and this zeta becomes like this. Then expression of this is follow this, and this is minus 20, and this is plus 20, and it goes minus 1 slope to this point. This is minus 20. It goes to this. It should go to this point, right? Because these values are same, and this slope is one is minus 1, the other one is plus 1. So they should merge at the same point. So this diffraction gain is 200, and you have pole here, and the second order system is coming in. All right? We know this frequency, okay? And we know this zeta. So we know equation of everything. So this zeta is derived from the phase margin of 45 degree, okay? Then take the inverse Laplace transformation of this. So first times input, first you multiply S domain expression of this one, and this is the TDS, and SS cancel, and you have inverse Laplace transformation of this thing. It's complicated, but it will separate into two terms. So one is this one. This is on this second order term is another one. So they have different coefficient. Okay, maybe they contain some S terms here, but we don't care about that. Okay, and this expression is not correct. This expression, something is missing here. Okay, maybe I was explaining that verbally, but it's not shown here. So I redraw this. So there are two terms. So this is the A terms and the B terms. Okay, let me have some space. You have space here, right? Previous page, right? So this is axis. This first term is exponential function. First term is obviously this is exponential function, okay? And maybe it has it starts with some number. So first one is this one. It decays exponentially. This is term number 1. And A is term A. And term B is sinusoidal waveforms. This is stable system. Okay, so because it is stable, it never grows. It is decaying somehow. So this is B. Right? The final result is A plus B is something similar to this. Let me use this color. Something similar to this. This one. Okay, but this time constant is determined by the dominant pole. So time constant of this tau is still 1/20. So TS 5% is still 3 times this one is 0.15 sec. 0.15 sec. Okay? You understand this, right? So this happens a lot. This happens a lot. In your some experimental work, you may find out you are observing something like that. So this origin of this one is very similar to the previous case. So in your transfer function, there are some peaking. Peaking like this. Peaking like this. And this one is not damped properly. phase margin of loop gain is very small, this will go up, and this AC component is very large, and your waveform will be like this. Okay. If they see this, they don't know what to do. They don't know what is the problem with this. Okay. So this is the problem of the loop gain. So by changing loop gain characteristic, you can change this shape, this oscillatory shape, but time constant, response type cannot be changed by just shaping loop gain. So the time constant is determined by the compensation 0, dominant 0. The first coming 0 usually determines the speed of the response. So you need to play with the two things separately. Okay, then you can control this. Okay, this is one example. The problem with this example is, first one is, this loop gain crossover frequency is too narrow. Can be increased, okay? And this has some oscillatory behavior. This has this, even though it has 45-degree phase margin, it has some peaking, okay? So this disturbance to output response will show some oscillation, all right? Oscillation is regulated by the low spec, right? So this will source of the EMI or something. So maybe you think that this is okay, my system is still working, but you cannot make them commercial product because of the EMI regulation. Then you need to kill all this unnecessary oscillation by some properly damping. Okay, for that you should know the problem, source of the problem first. So in this problem, we'll be using other type of compensation. Now you are asked to design the compensation to locate the 0 dB crossover frequency at this frequency while meeting the same specification as the case of the problem 3. All right? So, and show this everything, right? The design steps and the designs and so on. Okay? So we'll go one by one. This is a problem, okay? The one difference here is it starts with 10. So it has 10 here in the numerator. Previously, it was 1. It really doesn't matter. Any number can come here. So now we have 20 dB. So transfer function start from 20 dB, and it has one pole here and another pole here. And so the requirement is start with the integration structure and maintain -1 structure. It's the same as the select the simplest possible structure and locate 0 dB crossover frequency at this point to obtain 45-degree phase margin. So with this design compensation to get this loop gain characteristics. Okay, sounds like formidable, very difficult job, but extremely easy task, right? So this is a plan. Has 2 poles, then cancel these poles with 2 zeros. So place 2 zeros here. This 0, and these poles, they'll cancel. All right? And here is, this is 10, right? Then select integrator gain as 200. Then total integrator gain is this times this. So we'll have crossover frequency at this desired omega c. So just select this. Select these 3 numbers and structure. Okay? And place pole here. Here we have -2 slope. Okay? Then we have 45-degree phase margin. So we select this one. They comes from here, so it's known, and it comes from this specification, and place 1 pole, additional pole here to get 45-degree phase margin. Okay, if you don't put pole here, this is more desirable in some sense, but high frequency noise becomes big problem. At high frequencies, the noise is in the forms of this ringing and the spiking. So it contains a lot of high frequency harmonics. So you should attenuation at high frequency here. Eventually it goes down rapidly. So you need to have -1, -2 slope or -3 slope, something like that. For that purpose, you need to have one pole at here, then you will get 45-degree phase margin, desired phase margin. Previously, I said that you can increase the phase margin larger than 45-degree, very large value, 90-degree, but you are sacrificing something very much. Okay, this the high frequency degradation of noise rejection characteristic is 1. Okay, there are many others. So you put pole somewhere at high frequencies. So one good frequency is here. Maybe you are to add another one. Okay, if necessary, right? So final structure for the compensation is this one. So final structure for the compensation is this. So everything is determined. Okay, this is circuit, all right? This is sign changer, and there is a mixer, and you need integrator structure. Then you should have a capacitive path. So maybe you need 2 capacitors and 3 components. With this, you can implement what? Integration and 1 pole and 1 zero. Okay? So with this, one pole, A zero. All right. So the structure of this is determined. You don't want to use 4 elements here. And here, this R is required what? For what? Integration, right? For integrator, this is DC path of infinity impedance and DC path for the finite impedance. And without this, 1 0 is missing. So you place this here, 1 0 is created. Okay? So this generate integrator plus 1 0. Right? And select R1. You have 4. 1, 2, 3, 4. 4 components. But you should select 5. No. You have 4 parameters. 1, 2, 3, 4. Okay. But you have 5 components. So select this one arbitrarily. Okay. And with this, you know this. Omega m is determined by this. So integration gain is DC current is passing through this, and this. Okay? So integrator gain is given by this, and the 0 frequency, 1 over 0 is this one, 1 over 0. The impedance of this one, 0. Then it becomes final 0, and the parallel combination of this create a pole, but this pole is 0, which is this. Okay? Another pole is create parallel combination of this R times G2 plus in series with G3. That is the equation of series connection of capacitor. So this one is easy. Okay? Then you can calculate this one by one. Okay, and this is the final problem. Oh, this is not final problem. Sketch this TDS, right? So GS open loop is this, okay? And up to this crossover frequency, we use subtraction, and after this crossover frequency, it follows this, okay? So it follows minus 2 slope. If they don't match, if minus slope is here, so suppose for some case, this minus slope, minus 2 slope of this one occurs here, something like this, then it will be doing like this. Okay? Maybe it will create. So there is just some discontinuity, then this will create something like this. Suppose this is open loop transfer function, something like that. All right? So if they match here, then this is very easy. All right? They don't match, you should connect the jump. There's no jump, then if you plot real Bode plot, it will go smoothly like this. Okay? So now forget about this part. We are assuming this and subtracting this. This is 20 dB and this is 40 dB, and subtracting this from here, from 20 to 40, then this value becomes minus 20 dB. Right? This becomes minus 20 dB, and this passes this point. Okay, so this, because this is 20, this is a 10 times difference in between, then this line segment is symmetrical to this part. Right? Because this is minus 20, this is 20, and this is the 10 times difference in frequency, and then they should merge together at this point. So initial differentiation gain is 200. Okay, so this one is maybe the hardest part of this problem. Because you are not used to use this technique, and the remaining part is simple. Okay, there is a pole, another pole, 3 poles. Okay, so this is the equation for this transfer function. All right, this is very simple and graphical approach, and you don't need any calculation at all. Suppose you are doing this using this equation solver. You have this bunch of pages of result, which is usually. Okay, so this is the graphical approach, and this is kind of approximation, but very accurate. Okay, except this point, so on. And the problem of previous analysis, the problem number 3, or the merit of this new approach is omega c at higher frequency. Location of the omega c is at higher frequency. That will provide the faster input-output response. Another good problem is this noise to output transfer function is reduced further. So this, if sinusoidal noise is coming in, that noise will be reduced further. And if you take a look at this is slope change by 1. There is no second order term. There is no peaking. There is no oscillatory behavior in the disturbance to output transfer function or time domain waveforms. Okay? Final question is, somehow you decreased crossover frequency here. This was your original design, and this is your new design. Okay, but this pole 0 remain the same. Pole is still here. You just decrease the DC gain or integrated gain. So you have new polar plot of loop gain like this. So this is the pole is here. So pole remain the same. You just touch the one resistor and decrease the integrated gain. Then what will happen? To these items, phase margin will be increased, right? So phase margin at this point is 45 degrees. At this point is larger than that. So phase margin is increased and crossover frequency is decreased. Then speed of step input response will be decreased. And speed of step disturbance response is determined by this one. will remain the same. Okay? Oscillatory behavior somehow will be decreased because larger phase margin means less oscillation in the transient response. Okay? So as the final stage, you can play with location of this to change something. Usually that is not necessary. Okay? Okay, so this is end of this lecture and end of this semester. And I'd like to make a couple of final comments. I hope you use this, what you have learned this class to your research, right? You won't learn this type of analysis in other book, in other lecture, okay? Particularly the pole zero compensation realization becomes very simple, right? And you have this general picture of this feedback system. We start out from the very scratch, and we build up one by one, and all of them are necessary, but final stage is most powerful. Okay? For this final stage, design trade-off, you have learned all of these things. Okay, so I hope you will keep this for a long time in your research and some other study. Okay. Finally, next semester, I have one lecture about the modeling control of power electronics, PWM converter. Okay. Actually, I didn't learn this. I didn't learn all of this from the professors. My research area is modeling and control of PWM converters. And during that course, when I was studying in the United States, I just audited the senior lectures and the graduate lectures and the mathematical lectures. I just audited, and somehow I combined with my research area, and I could generate this story. So this story is way different from the other courses about this. I think so. I'm not sure. Okay. All right. And I hope you enjoy this class as much as I did. And if you are interested in power electronics, I strongly recommend to the following courses. Okay. With this background, then that story will become much easier. Okay. For the power electronics student, if you try to learn this by yourself, maybe it took 20 years. There are so many garbages and one paper. Partially they are okay, but they are not providing one coherent story. Right? So this might be a good chance to become expert in this area. All right? Okay, thank you. Okay.